Okay, let's go and take out this homework. So oxidation numbers and cations, and for the anions, and then the nomenclature for this. So who's the cation? What's its charge, and tell me why.
Hydrogen.
Why is hydrogen the cation?
Because it always is unless in combination with one of the I'm blanking right now. Something that's highly electronegative.
It's negative when it's with a metal.
It's negative when it's with the metal or boron. So if it's not with metal or boron, then it's positively charged, and its charge is +1. Okay. And then the cation? We really have no options other than chloride being -1. If I know for a fact that the hydrogen has to be a +1 and that chloride has to be a -1, then you're finished. And so what's the name of this?
Hydrochloric acid.
Seriously? What is going on? Alright, hydrochloric acid. And how about our next one?
Yeah.
Cobalt's the cation. We don't have a charge for the a set charge for the cobalt, but we know it has to be the cation. For what reason?
Because it's a metal.
Because it's a metal, and it can't be the anion. So then my sulfur is my anion, and I don't have a set number for sulfur, but since this is an ionic compound, this is just a salt. How do I determine sulfur's charge?
It's in the oxygen column.
It's in the oxygen column, so it's -2. So that forces the cobalt to be +2. And so what's the name for this?
Cobalt 2 sulfide.
Wow. Why is it doing that? It's kind of driving me crazy. What about that? What about that? All right, we'll see if that changes. Yay. We okay with cobalt 2 sulfide? All right, the next one?
Hydrogen and cation.
Hydrogen is one of the cations.
That was the sulfur.
The sulfur is going to be the other cation because the oxygen is the anion, and they're each -2, so there's 8 of those. So I've got -8, and so I've got +1 from the hydrogens, and so then the sulfur needs to have a 6 charge to cancel all that out. And what's this substance?
Sulfuric acid.
Sulfuric acid. Okay, next one. Who's the cation?
Iodine.
The iodide is. How do I know that iodide is?
Because it's with oxygen.
It is with oxygen. So the rule on the halogens is they're a -1 charge unless they're with a halogen that's higher on the list than them, another halogen, or they're with oxygen. So this is with oxygen. So oxygen gets to be its normal -2, and then the iodine is whatever the oxygen did to it, which is what?
It would be +7.
+7? It needs to be a +7 because if I've got -8 from the 4 oxygens, I need to only cancel out 7 of those charges because the per iodate needs to have a -1 charge because it's a polyatomic ion. And so there's a name. Everybody okay with per iodate? So what's the 8 part mean?
More.
More, and then the per part?
More.
More. Okay. So we got more oxygen. Excellent. Last one here. Who's the cation and why? The manganese is the cation because it's a metal, and the iodide must be the anion. And since the iodide is a halogen and it's not with another halogen or an oxygen, its charge is -1, and so then the manganese must be a 3. So manganese 3 iodide. That good? If a molecule is polar, what's occurring? What types of molecules can be polar and which cannot? So what's happening with a polar molecule?
All the electrons are staying around one side of the
They're uneven.
structure. The majority of the electrons are on one side.
So it gives it a slight.
Why?
There's electronegativity
Right.
is greater than 5.
That's how you know, but what's actually physically happening?
It's becoming slightly charged on one.
They're sharing the 2 electrons.
Say that again?
They're sharing the 2 electrons.
Unequal.
Unequally. It's an unequal sharing of the electrons in a bond. So if it's unequal sharing of electrons, what molecules can be polar? So only the covalent ones can be, because covalents are the only ones that share. So I can't have uneven sharing in an ionic compound because there's no sharing at all. All right, these last two. All right, so I've got 4 here, 1 here, and 7 here. So this is times 3. So I have 14 electrons to deal with. Are we okay with that? So why am I going to put carbon in the middle?
Because it can make the most bonds.
Okay. I'll just throw some hydrogens around here, and then my fluorine on there. And I've used how many electrons? I have 6 left, which is good because the fluorine needs 6 more electrons. All right, so I've taken care of my Lewis structure, and now my question is this thing going to mix with water? Do I want the 3D structure as well? I do. Is there a Vesper structure for this one? There is not. Tell me why.
There's no lone pairs of electrons on the central.
There's no lone pairs of electrons on the central. Okay, so what's the molecular structure, or the 3D structure, going to look like for the molecule? All right, so hydrogen, hydrogen, fluorine, hydrogen. So tetrahedral. And is this guy going to mix with water or not? Yes.
Can you say again why there's not a Vesper structure? Because there's no lone pair on the central?
Because this carbon has just bonds on it. The only time a Vesper structure is applicable is if the central atom, any atom that's got more than one actual connection to a different atom, if there are lone pairs on that, then you'll have a Vesper structure. So all of the atoms in this molecule have one bond, except for the one in the middle. And so the only one that could have a Vesper structure is the carbon, but there aren't any lone pairs on it, so then there isn't. So yeah, this thing's going to mix with water. How come?
Because the fluorine is pulling all the electrons to the side.
So the carbon's electrons in that bond right there are, that bond right there are going to be drug over towards my fluorine. So that's going to end up giving me a partial negative on this side of the molecule. and a partial positive on that side of the molecule. So that thing will be able to mix with water. Okay, so I've got 5 electrons here plus 3 times 7 electrons here. So I have 26 electrons to deal with my nitrogen triiodide. So I'm going to put the nitrogen in the middle. Bond, 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 I. And then I'll throw electrons up. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I've used 24 of my electrons, and I'm going to put my last 2 right here on this nitrogen. And so there's my Lewis structure. So can there be a Vesper structure for this one?
Yes.
Sure. That central atom has more than one thing on it. So the Vesper structure for this is going to look like what? No. No, that's the molecular structure. It's a tetrahedral. That central atom has 4 things around it. One of them is a lone pair of electrons, but there are 4 things around that taking up position. The reason that those iodides are down and being pushed away into a 3-dimensional structure is because there's a lone pair of electrons on top of the nitrogen. They would be in a flat, planar structure if those 2 electrons weren't there. So that dramatically changes the molecule. It switches it from being nonpolar to polar. So here's my my Vesper structure. So what's my molecular structure look like? Trigonal pyramidal. So nitrogen, iodide, iodide, iodide. So the lone pairs of electrons disappear, and now I ask myself what's left. And it's pyramid shape, but since it's a triangle, I have to designate that it's trigonal pyramidal. And I already said it was going to mix with water. What's the reason behind that? Not just the lone pairs, the electronegativity difference here is going to cause this side here to be negative and this side here to be positive. It's closer to fluorine. Yeah.